Class example 3.17 is a classic application of an exponential equation. Here, we're told that a particular investment fund has doubled in value over 5 years. We assume that the fund continues at this same rate of growth and are asked to set up and algebraically solve an equation to determine how long it will take to grow to $80,000. Now, I'll point out that this is actually a problem you could solve using just your fingers. If it takes 5 years for 5,000 to double, that means in 5 years it goes from 5,000 to 10,000. And then 5 years later would go from 10 to 20,000. And 5 years later would go from 20 to 40, and then from 40 to 80. That is 4 periods of 5 years. So I bet you the answer is going to be 20 years. Let's see how we can do this with an algebraic equation. We'll start with the formula that's given to us on our formula sheet. It says y equals a times b to the t over p. In this, the y is our final amount. The a is our initial amount. The b is the base of the power. That's how much we're multiplying by. In a question where we're talking about doubling, it will be a 2. Tripling, it would be a 3. If we were talking about halving or a half-life, it would be 1/2 or 0.5. The t and the p are often confusing for students, but the p is what we call the period. So that's how frequently the doubling happens. In this case, that will be our 5. The t is how much time has elapsed in a particular case. I'd like to point out that a finer way of understanding this is to recognize that the y variable and the t variable are our dependent and independent variable respectively. And a, b, and p are parameters, which means y will change as the amount of time changes, and t will change as the amount of time changes, but a, b, and p will be fixed for any given scenario. Here we see that we put our starting value at 5,000 and our final value at 80,000. We replace our growth factor with 2 because we're doubling. If you recall from Math 20 any instance where you worked with 1 plus I, as in 1 plus the interest rate, here our interest rate, or our rate of growth I should say, is 100%. So 1 plus 100%, which as a decimal is 1, gives us the 2. Our p for period is that 5 years, so we write that as the denominator of the exponent. Once we have isolated our power term by dividing both sides by 5,000, we recognize that 16 and 2 can both be written with a common base of 2. We write 16 as 2 to the 4, and then say because the two powers are equivalent and have the same base, that the exponents must be equivalent. So 4 must be equal to t over 5. Multiplying both sides by 5, we find our answer to be 20. We can check this answer in our calculator by replacing the t value with 20 and noting that the output is 80,000. If this were a word problem, recall that you should always write your answer including the units. I'd like to show you how to solve this problem graphically now, but it might seem a little bit frustrating. Bear with me and I'll explain why. I'm going to input as our y1 value 80,000. That's our goal. I'm then going to input as our y2 value 5,000 times 2 to the x over 5. Here the x is taking place of the t. So this represents the left side and right side of our equation. We already know that the answer to this question is 20. But you'll note that by default our window settings only go from -10 to +10. So when we press second calc intersect, we should get an error message. Here it says no sign change. That means it can't find the answer. And that's because these two functions have not intersected within the given domain. By increasing our x and y values, by increasing our x maximum value, we allow the answer of x equals 20 to fall within the given domain. But you'll still notice we don't actually see the intersection point. A lot of students want to see this, but recognize that it is intersecting at a y value of 80,000. So if you do want to see it, you would need to replace your y maximum with a number larger than 80,000. But importantly, that's not necessary to find the solution. However, it is necessary that the x domain, so x min to x max, includes the x value you're looking for. On the previous slide, I mentioned that when you're solving for a point of intersection, you don't need to be able to see the intersection point. However, a lot of students find this frustrating. So, an alternate approach is instead of graphing the left side of the equation as y1 and the right side as y2, subtract the right side from the left side and write that expression as y1. Then, wherever that is equal to 0 will be your solution. So you can calculate that one of two ways. Make y2 equal to 0 and use second calc intersect, or simply calculate the 0 of y1. Here we see in both cases it will show that answer as being 20 and 0. I'm a big fan of solving graphically because seeing the solution is often a good confirmation that you've done things right. But if you're using a Texas Instruments calculator, there is another method, and it's called the solve function. To access this, you'll press the second button and then 0. This will take you to the catalog menu of your calculator. Here, every function of your calculator is listed in alphabetical order. You can now either press the natural logarithm button, or ln, or the number 4, and this will jump you to the menu, to the letter S or T. From there, scroll down or up, depending on which letter you pressed, until you find the word solve with an open bracket. Once you've selected the word solve by pressing enter, you'll need to input 3 pieces of information for your calculator. The first is an expression equal to 0. That usually means that you take the left side of the equation and subtract the right side of the equation. Here we show 80,000 minus 5,000 times 2 to the x over 5. Then you press the comma button. The comma button is found above the number 7. You then input x, telling the calculator, I'd like you to solve for the variable x. You then press comma again, and now you must insert a guess. Now, you might be asking, what do you mean a guess, and what number should I guess? And the answer is, if there were multiple answers, the calculator would find the answer closest to your guess. If there was a discontinuity or a vertical asymptote, for example, and you were on the opposite side of it with your guess from the solution, that would give the calculator problems. But for any graph with an unlimited domain and only one solution, it doesn't really matter what value you put in. Here we guessed 0, you could have guessed 10, you could have guessed 40. In all cases, once you press enter, the calculator will say, your guess is incorrect, the answer you wanted was 20. I'll point out that this is an excellent method if you know there's only one solution. However, in most cases, it's better to go with graphing. The advantage of this one, however, is you don't need to mess around with window settings, adjusting them when things are outside of your given domain.